Hi guys, welcome once more to my YouTube channel. Today we'll be solving unique parts. Our last video we did maximum subarray, which was a very interesting dynamic programming question. We got to identify patterns and arrived at an optimal solution. I'll be putting the link in the description box and also in the video so you can click and go back and watch. Please guys, don't forget to share, subscribe, don't forget to comment, don't forget to like the videos. Share it with your friends so that we'll get to have a large community of people solving LeetCode and correlating questions. So let's dive into unique parts. As we all know, we are always doing what, why, and how. So let's start with the what. So what is unique part? Unique part, as you can see, is a medium LeetCode question. It has a lot to do with dynamic programming, which you get to see. There is a robot of an M by N grid. Right, then this is the number of columns to the number of rows. The robot is initially located at the top left corner. That is the first grid. You can see grid index 0 and 0. The robot tries to move to the bottom right corner. The robot is moving from this corner to this corner. You can see there's an image of a robot here. This is his finishing position. So he's moving from here, which is the top left, to the bottom right. This has an index of 0 and 0. This has an index of n-1, n-1. The robot can only move either down or right at any given point in time. So the robot can only go either forward or down. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach in the bottom right corner. So the test cases are generated, so the answer will be less than or equal to 2 times 10 to the power 9. So all you're supposed to do is to give you m and n, which will represent the dimensions of a grid, and I'm supposed to provide the number of possible unique paths that it can take the robot to move from this first index to this last index, right? So what that means is, okay, we are given an example. So yeah, this one is very long, so I think it takes us time. Let's take a 2x2 grid, right? So m is equals to 2, n is equals to 2, right? So it means you have something like this. You have so you have this, and I'm supposed to move from this first index to this last index. Now, how many possible ways can you do? So one, you can either move from 0, 0, then you go right. When you go right, you have 0, 1, then you go down. When you go down, you have 1, 1, right? Or instead of going right, you go down. So this means you have 0, 0, or you have, when you go down, you have 1, 0. Then now this means for a 2x2 grid, you have 2 unique paths, right? Now let's go on to do something a little bit more complex, right? Or we can just use this example. So we have 3x2. So we have n is equals to 3, n is equals to 2. So that means you have 0, 0. So number of rows should be 3, number of columns will be 2, right? So this your grid. Okay, so unique paths. So you move from the first index, which is index 0, 0. You can go down. So let's go down. When you go down, you have 0, 1, or rather you have 1, 0. Then you have 2, 0. Lastly, you have 2, 1. Right, so that's 1. Now, either you come straight down, or let's say you come 0, 0, you come down again, you go to 1, 0. Now, instead of coming to 2, 0, you take 2, you come down, you go to your right, you will have 1, 1. Then you go down, you have 2, 1. This is another part. And I think lastly, when you can go to the right, you will have 0, 1. Then you can just come straight down. When you come straight down, you have 1, 1 also. Then you have 2, 1. I think this is how the number of possible ways you can generate. So for a 3x2 matrix, you have 3 unique parts, right? So this is basically how to get unique parts. So I would suggest, if this is unclear to you should go back and try doing this on your own. You can try doing for a large size of array like this so it get clearer, right? So, but this is basically what we're trying to do. We're trying to get the number of unique parts that you can generate from a matrix when your robot wants to move from the first index to the last index, right? So we have constraints. We are being told that m and n will be ranging from 1 to 100. So that's enough for the words. This should be a clear description. You'll be giving 2 integers m by n, which is signifying the number of rows and number of columns. The given matrix, we are supposed to return an integer, the number of unique paths that a robot can move from the top left corner to the bottom right corner. So let's dive into the why. I'll also be dropping the link to this Medium article in the description box. You can go and read it if you feel the video is too long for you. The main thing is you understand. This is what I've already talked about. The words we have described this, we have taken examples. These are examples of a 3x3 grid. You can also do this if you get unique parts, right? So why? Fundamental dynamic programming concepts. As a software engineer, unique parts is a classic dynamic programming problem. It helps you break down complex problems into smaller sub-problems, right? It helps you to learn memorization and tabulation to optimize solutions efficiently. This problem trains your ability to recognize overlapping sub-problems, repetitive calculations that can be stored for efficiency, and optimal substructure. These are essential problem-solving skills that are required in technical interviews. So even if you go to LeetCode, dynamic programming filter, you get a lot of questions on dynamic programming, and this will be training you for technical interviews as a software engineer, right? In the real world, just like it is being used for a robot, you use it also for robotics and autonomous systems. It's basically using pathfinding, right? So like self-driving cars, Google Maps, you get to wonder why I'm moving from point A to point B, and they try to give you about 5 different routes, but they will give you the shortest route, which will save you time and be optimal. So yeah, so self-driving cars, your Tesla uses something like this. Google Maps also uses an algorithm like this to find location between the place and the place, right? Inventory management and logistics, just like this, it's also in pathfinding. So you get the efficient way to retrieve or deliver items from warehouses. Right? Companies like FedEx and UPS, which are known for delivery, they use this algorithm to optimize their delivery routes. For network and load balancing, right? It is also used in distributed computing to efficiently distribute requests across multiple servers, improving performance and resource allocations. When you have servers scattered all over the world, whenever it is put in, you have to pick it from the closest server instead of traveling a whole lot. So these are the applications of unique parts. So for the how, for a brute force, which we won't be even doing today, but I think we'll just discuss about it. Using a brute force, you can say, okay, what you want to do is, so you'll be looping from the beginning to the end, right? You can use recursion. You'll be adding 1 to each index as long as it doesn't get to this, right? Whenever it gets here, you add your unique parts and see the percentage to give you when you submit. But that's the first thing you should think of, right? So when you are here, you add 1, you come here. You can either add 1 to here or here to here. So you come here, you go there, you add another 1, you add another 1, you add another 1. You keep adding until you get to the last one. When you get to the last one, you increase, obviously, variable you'll be keeping outside the loop, which is your number of unique parts. You increase it by 1 whenever I get to the finish line. Whenever all your instances get to the finish line, you increase by 1. So you have a total number of unique parts which will return after all the loop. So yeah, but what to be using is a dynamic programming approach, just like we did for maximum subarray. So what we'll be doing is establishing relationships between unique parts of each box here, right? What this means is for the first row and the first column, the unique part to get to this is 1. The unique part to get to this is 1. You can pre-fill the first rows and the first columns. They have constants. They have a simple unique parts for each index, right? However, for this grid, right, the unique part for this grid is equals to the sum of the unique parts for this grid and this grid. Just follow along. The unique parts for this grid is equal to the sum of the unique parts for this grid and this grid. So what I've been trying to do is just say the unique parts, let me call this. So unique parts for grid I and j is equal to unique parts for I minus 1 j plus unique parts j minus 1. This is I, then j minus 1. We have to confirm that this formula is actually good. Unique parts at every index is equal to the sum of the unique parts at the indices before that index, right? So the unique part at I and j is equal to the unique part at I minus 1 of j plus the unique part of I j minus 1. So that typically means the unique part at this finishing index is equal to the unique part at this index plus this index. The unique part at this index is also equal to the sum of the unique part at this index and the unique part at this index. So let's use a basic example. Let's use this, right, to explain. So we call this example 1. So I'm doing unique part at each index, right? So we have 0, 0. I mean, obviously the unique part at the index will be 0. So take note that the unique part at all the rows and all the columns, that the unique part at every element aside the first element on all the rows and all the columns will be 1, because you only have one way of getting there, right? For this box, you can only come through this part since I'm moving only forward and down. For this box, you can only come down. So everything here is 1, 1. So let's say at 0, 1, you have 1. The unique part at 1, 0, you have 1. The unique part at 2, 0, you have 1. So 0, 1 is this box, right? You can only go 1. 1, 0 is this index right here, this element right here. You can only go 1 also. 2, 0 is this element right here. You can only go 1. Now where you start applying this is from this and this. And that's for this, which is at element 1, 1. So the unique part here will be equals to sum of the unique part at 0, 1 plus the unique part at 1, 0, right? Which will be equals to 1 plus 1 to give it 2. The unique part at this index, which is 2, 1, will be equals to the sum of the unique part at 1, 1 plus 2, 0, right? So this will give you 1 plus 2, which will be 3, which is the same thing we got here. All right, so let's solve this. Let's use this. So this is a little bit more complicated. So let's do example 2. So for example 2, now we have, okay, we have m is equals to 3, n is equals to 7, right? So we have 1, 2, 3, 4, 5, 6, 7. Is it 6? 1, 2, 3, 4, 5, 6, 7. Yes, 7. So we paste down this 3. So this is what our grid looks like, right? We are going to be finding the unique part at each index. Remember that I said for the first row and the first column, everything will be constant. I mean, except this first one, everything will be 1, 1, 1, 1, 1. So that's 0, 0. I mean, I don't think 0, 0 should be even be 1. Let's say 0, 0, 0. I'm unsure about this, so I can confirm. Maybe 0, 0 is 0. Maybe 0, 0 is 1. But I believe 0, 0 will be 0 because you're not moving anywhere. I basically start standing. But well, let's do 0, 1. For 0, 1, you have 1. For 0, 2, you also have 1. For 0, 3, you also have 1. For 0, 4, you also have 1. For 0, 5, you also have 1. And lastly, for 0, 6, you have 1. So this is the first row, right? This is the first row. You have 0, you have 1. Because like I said, you can only move 1. You only have one unique part to come to this element. You also only have one unique part to come to this element. We will also feel the same thing for the first column. We have 1, 0, which is 1. Lastly, we have 2, 0, which is 1. So after this, all we need to do is start calculating for these boxes, and everything will sum up down to this. So we start with this, right? This is 1, 1. So for 1, 1, you have 1, 1, 0 plus 0, 1. Please take note, this is unique part at unique part at unique part at unique part at. I'm just, since I'm writing it, it's little variables. Just pay attention. Okay. So for this, you have 1 plus 1, which is 2. For the next element, 1, 2, which is this. It will be this and this. So you have 1, 1, which we just calculated, and 0, 2. So you have 1, 1 plus 0, 2, which is 2 plus 1. So this will be 3, right? So for 1, 3, you have, okay, we can only do the looking at this box. Since we are just subtracting 1, we can just have it here. So you have 1, 2 plus 0, 3. So this will give you 3 plus this is 4. Okay, so I can just copy and paste this down. So for the next one, which is 1, 4, we'll be getting 1, 3 plus 0, 4. This should be 4 plus 1 to be 5, right? For our next item, which is 1, 5, we'll be having 1, 4 plus 0, 5. This is 5 plus 1. This is 6. On our last item on the row, we have 1, 6, right? For 1, 6, you have 1, 5 plus 0, 6. This will give you 6 plus 1. The unique part for that element is 7. Now we're done with this row. We have to go to the last row. So for the last row, we're starting with 2, index 2 and 1. For 2 and 1, you have 1 and 1 plus 2 and 0. So for 1 and 1, we got 2. For 2 and 0, we got 1. So this is 3. For 2 and 2, you have 2 and 1 plus 1 and 2. So for 2 and 1, it is 3. For 1 and 2, it is 3 also. So this is 6. For 2 and 3. So for 2 and 3, you have 2 and 2 plus 1 and 3, right? For 2 and 3, 2 and 2, we got 6. For 1 and 3, this is 1 and 3, we got 4, which is 10. For 2 and 4, which is okay. You have 2 and 3 plus 1 and 4. 2 and 4 you got 10. 2 and 3 rather you got 10. And for 1 and 4, 1 and 4 we got 5. So this is 15. For 2 and 5. For 2 and 5 we have 2 and 4 plus 1 and 5. For 2 and 4 we have 15. For 1 and 5, which is this, we have 6, which is 21. Lastly, for 2 and 6, we'll have 2 and 5 plus 1 and 6, which will be 21 plus 7, which will give us 28. So the output is 28. So what we're doing is we're just calculating everything, then we're returning the unique part of the last element, which is this. So this means we'll be creating a new grid, right? And we'll be having these values. So 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7, right? For the next one, we have 1. This also, we have 1. So this will be 2, 3, 4, 5, 6, 7. This will be 3, 6, 10, 15, 21, 28. So this is what our grid will look like after solving this like this, and all you need to do is just return this last element. So you can try doing this. If you don't understand, try, like I always say, solve it yourself. Write a grid. You can do 100 by 100, which I believe is too much, but get a random grid, right, and try doing this. You will definitely arrive at this answer. It's really important for you to understand the logic and what's happening. So yeah, so with this, all we need to do is just write our pseudocode. So you first initialize array with okay, so you fill in to be 1, right? After this, you calculate the unique part for each index. So for this, you'll be using this formula. Then what you'll be doing is, after everything, you return. So this is all what we're doing. So you can dive down to the solution. Or should I call this? Let's call it CQ, which means unique parts. Right, so this is new int. Right, so we'll put this as equals to 0. So let's say fill up first row. So for int I, should be I less than, your number of rows will be n. Right. So I plus plus, what we're doing is doing uq first row I plus to 1. Okay, and also fill up first column. So for int I equals to 1, the number of columns is n. So we have I plus plus. So you have uq. What you have here will be I, this is 0, this will be 1. So after this, all you need to do is we fill up the rest of the grid. So we'll be looping from 1. There's this column, we start with it. We are starting with 1, 1. So I and I plus plus. And also we're having an inner loop, right? J and J plus plus. Okay. So what we're doing is uq of I and j equals to uq minus j plus uq j minus 1 I. After this, all we're doing is we're returning the last element. So we return uq n minus 1 minus 1. Right? Okay. So let's see. Oh, this is supposed to be a comment. Okay. Something is wrong. So was it? I don't think this is it. So I don't think this is it. Oh, it's supposed to be like this. Okay. Okay. So I guess we have to change this, and we also have to change this. Oops, that was a lot. So yeah, so this is good now. Let's try something. Okay, something is wrong. Oh, so this solves what I was confused about. So it means when I'm giving a 1, this is supposed to be 1, not 0 then. I mean, which is still weird to me. So I can just put this as 1. Okay. So this is 100%. This is a good start. That sums it up, right? You can go and practice this. There are more questions you can solve related to this. Minimum part cost in a grid, minimum cost homecoming of a robot in a grid dungeon game. This is hard. I'll also put the link of this code in the description box. I already have a GitHub repository that will contain solutions for this. It should just be one of them. So yeah, thank you guys. Please remember to like, share, subscribe, comment. I want to know the optimized way you think we can solve this. And also try the brute force approach, which I explained earlier, right? I think you can use recursion to solve this. I just think it will run slower than this. So yeah, thank you guys. Have a nice day. See you next time.